This is problem 11 of the QHack 2023 Quantum Coding Challenges, and this one is entitled The Change of Qubit. And what we're being asked to do is to, for a 3-qubit system, swap this first qubit, which has an arbitrary state psi, to the last qubit. Now we're giving a few restrictions. The first one is that we can't utilize gates for qubits that are not adjacent to each other. So we can only apply gates between qubits 0 and 1 and 1 and 2. And the other caveat is that we're told that we can implement a circuit on the left and a circuit on the right, but in between there will be an error applied where at random a poly X gate is introduced. So we need to figure out how to perform this swap, taking into consideration that now we have an error introduced in our circuit. Now, when we have errors introduced at random, the first thing that comes to mind is that we need some sort of error correction mechanism, right? And typically what we want to do is just perform an entanglement between our arbitrary state psi with the extra qubits we have, so that we have some level of redundancy, right? So now we have copied here this state alpha 0 beta 1 to alpha 0 0 0 and beta 1 1 1, right? Now the problem is that if we were going to perform the conventional bit flip error correction, well, we would need to take a majority vote, right? So if we, for example, now introduce this random error where this X gate can be applied to any of these qubits, well, the possible states that we have are alpha 1 0 0 beta 0 1 1, alpha 0 1 0 beta 1 0 1, and alpha 0 0 1 beta 1 1 0, right? So we have 3 possibilities, and what we would do is take a majority vote, see which is the most common occurrence of a bit, and then flip the other one. But for that, we would need ancillary qubits, right? We would need some additional qubits here to perform these operations, but we don't have that available. So since we are guaranteed that this poly X error will be applied to one of the qubits, one thing that we can realize is that, well, if we apply Hadamard gates in between where the error can occur, well, since sandwiching an X gate between Hadamard gates is equivalent to a Z gate, well, we've turned this bit flip errors into phase errors, right? So now we're, instead of applying a random an X gate, what we're doing is applying a random a Z gate. And when we do that, well, we don't have any bit flip, we only have a phase flip, and the phase flip occurs whenever we're applying the Z gate and the qubit is 1. So in all 3 cases, we're gonna have the same state. So here, actually I have a mistake. Here's all, this 3 are 0 0 0, and these ones are minus beta 1 1 1 in all 3 cases. So we converted an error that could be occurring on any possible qubit to a phase error that is always the same. So how do we correct for this? Well, it's as simple as just applying now a Z gate into any of these qubits, right? So if I apply it to, let's say, qubit 0 here, what we're going to have here is now, well, we're just gonna flip the phase of the 1 1 1 state, right? So we're gonna have here alpha 0 0 plus beta 1 1 1. And even if we apply it to qubit 1 or qubit 2, it's going to perform the same operation. So now we have corrected for this possible error that could occur. So now all we need to do is apply CX gates in a way that we end up with state 0 here at the top, state 0 here at the bottom, and state alpha 0 plus beta 1 here in the last qubit. And to do this, well, it's as simple as just applying a CX gate between qubit 1 and qubit 0. And that's just going to flip this qubit right here, right? So that will give us alpha 0, 0, 0 plus beta 0, 1, 1. And then if we apply a CX gate between qubit 2 and qubit 1, that flips that second qubit. So then at the end, we're gonna have alpha 0, 0, 0 plus beta 0, and then this one gets flipped 0, 1, right? Which is the same as 0 tensored 0 tensored alpha 0 plus beta 1, which is what we wanted to obtain. So let's go ahead and implement this in PennyLane to see the result. So as always, we import PennyLane and NumPy. And we were told that we need to split this into two separate circuits, one to the left of where the error occurs and one to the right of the error occurs, right? So first we define a circuit on the left, and this is going to have, as we show here, well, this part of the circuit, right? So there's two CX gates and the Hadamard gates, and then the circuit to the right is going to have this Hadamard gate, the Z gate, and the last C0 gates. So on the left, we have the two C nodes. Then I'm going to use this broadcast for the three Hadamard gates we need. And then I'm just applying a barrier so that when we draw the circuit, it's easier to follow. Then we're going to define our right circuit. So define circuit right. And I'm just going to copy and paste the code I have already here, which has, again, a barrier just to make it easier to draw, using broadcast to apply the Hadamard gates, the poly Z, and then the C nodes that we need to guarantee that state psi is in the last qubit. And then I'm just going to copy and paste some of the code that was given to us, which is responsible for applying the U gate, which is that error at random, and then just constructing the Q node. So this is the code for the random gate, and then define the device, and then the Q node, which applies a U3 gate that is just to initialize the state psi with some alpha, beta, and gamma. Then applies the circuit on the left, the error, and then the circuit on the right, and then returns an expectation value with some observables and some operation on them. So now if we go ahead and take some angles that we need to feed to this U3 initialization gate, and go ahead and print or draw our circuit and print the result, we see here that we have this U3 with the angles applied, then the two CX gate, the Hadamard gates, then I have the barrier here, and in this particular case, the error was applied on qubit 0, then the Hadamard gates, then that poly Z, and then the CX gates that will guarantee that this state will be on the last qubit. And here, again, this was applied at random. If I run it again, it was applied to qubit 0 again. Let's keep trying until, yeah, now it's applied to qubit 1, now to qubit 2, now to qubit 2 again, qubit 1. So yeah, it's applied at random. As you can see, we always get the same expectation value. And if we go here to the problem itself, we see that for those angles, we are supposed to get minus 0.97322. Now let's change those angles, and we expect to get 0.88563. So that's another example, another input to verify our results. And here we have it 0.88563. I think they give us more examples here. So this should be 0.457. So, and here we have it 0.457. So hope this was helpful. Let me know if you have any questions.